Hello everyone. So today Eliz will give us a simple proof of the Gauss Reciprocity law. And let me introduce Eliz to you. She will start her third year in the Galatasaray University. And I think you can start it.
Okay. First of all, I would like to thank everyone who helped me take part of in this project, and of course my mentor, who was always there for me during the process. Before the tools required for the theorem, I would like to talk about the historical process of the theorem. Our first picture is Euler. The quadratic reciprocity theorem was first stated by Euler, and after Legendre formulated in modern form. And after this too, in 1801, Gauss published arithmetic discussion. This was his work that he introduced to modern notation of congruence. And moreover, he gave the completed proof of quadratic reciprocity law in this work. And his lifetime, he published 8 distinct proofs. But this wasn't end. The development of the theorem did not stop there. After Gauss, about 200 more proofs have been published. But today we are gonna give the proof of Eisenstein. And if you're interested in the theorem, you can find all the proof in here. There's a list, and there is a link into this text. And we talk a little bit about the theorem. I will now describe some of the tools needed to prove the theorem. First, I want to give a definition. We call A is a quadratic residue modulo M. If there's a such congruence has a solution. If we cannot find such an X, A isn't a quadratic residue. After that, I would like to explain the Legendre symbol. Let P donate an odd prime. The result of the Legendre symbol can be 1 or -1, and the result depends on whether A is a quadratic residue in modulo M. And we can pass our main theorem, Gaussian reciprocity law. Let P and G be distinct odd numbers. When we multiply this to Legendre symbol, we are gonna have 1 minus 2 P minus 1 over 2 times Q minus 1 over 2. And this is gonna our main theorem. And mathematicians have wondered about the easier computation of the Legendre symbol, because sometimes we can compute very easy, but sometimes it's harder. And the connection between the Legendre symbol. So the quadratic reciprocity gives us a connection between the values of Legendre symbol like this. And for the different odd prime P and Q. And now I want to explain Gauss Criterion. Let P be an odd prime and A be an integer that is not divisible by P. And we are gonna create a list of integer like A, 2A, 3A, etc. When we reduce these numbers to P, some of them gonna be positive and some of them gonna be negative. We will call the number of negative ones mu AP. Just we are gonna take the negative ones. Then we have this relation. We will not prove this theorem because of the time duration, but we will accept the result to prove the reciprocity law. And this is the last thing before the theorem. I would like to explain a lemma. Let P an odd prime and A be an odd integer that is not divisible by P. Then we have the summation I just want to explain the floor function. Maybe there's someone who can't remember this. Basically, we just take the integer part of in the floor function. For example, maybe we can take 3.5. The floor function, when we take the floor function in 2.5, it's gonna be 2. Take this lemma for the proof. Then we are all introduced all the tools needed to prove quadratic reciprocity, and we are going to use a little geometry for the proof. Let P and G be odd prime, and we consider the triangle T in the Cartesian plane, and we will find the points inside the triangle whose coordinates are integer. When we look at this, we can just compute the points whose coordinates are integer. So it's easier to see that the result, and we are gonna make an example. And as we can see, the hypotenuse of the triangle has a slope Q over P. So we can describe the line, this line, like y equals to Q over Px. So for x equal to 1, we get integer part of Q over P. And for x equal to 2, we get integer part of the 2Q over P. And this is going to be continued this way. And also notice that there are no integer points on the diagonal line of the rectangle except for the point 0, 0. Because of the slope, this line is Q over P, and we just assume that these primes are not multiply each other. Specifically, we can say that number of points with integer coordinate Q in the triangle T is gonna be the summation. And after this, when we create another triangle like T prime, it's just the same triangle, but it's a symmetric one to another. And when we put them together, those triangles together, our geometric image is gonna look like this. And this is a rectangle, of course. And in this state of the figure, it's become easier to calculate the points whose coordinates are integer. And rectangle has integer part of P over 2 column of the integer points for the integer points. And each column contain integer part of Q over 2 integer points. And so number of the integer point in this rectangle gonna be this. So if we combine the formula from our lemma, we are gonna have this equation. Maybe it's not for real numbers. Let P is 17 and Q is 11. When we take our formula, we just take the K is 1 to K is 5, because our Q is 11 and Q minus 1 over 2 is equal to 5. So we have this summation, and when we add all the summation, I just make an example. For example, integer part of 70 over 11 is of course gonna be 1, and integer part of 34 over 11, it's gonna be 3. And when we going to same way, we are gonna have 21. And when we continue for the P, our P is 17. And for this summation, we take the key is equal to 1 to 8, because 70 minus 1 over 2 is 8. And when we calculate all these numbers, it's gonna be 19. And it is the same thing the rectangle has 40 points because it's the same formula, p minus 1 over 2 times q minus 1 over 2. When we take this, we have 14, and when we add these two numbers, we have 14 either. So it's okay when we see the rectangle, it's the same result. Now we are going to calculate our muse for mu 17 and 11 and mu 11 to 17. For our first mu, we have to check the list 17, 44, etc. For the modulo 11, and then we already give the definition of mu, and we know that in this list, some of them gonna be negative and some of them just gonna be positive, and we just take the negative ones. And for this, for example, 17 is minus 5 in modulo 11, and when we gonna take same path, we have just 3 numbers who is negative. And for other mu, our list is gonna look like this. And when we consider this list for modulo 17, then we can see 8 equals to 40 in modulo 2. Since we saw the relation between mu and the integer points in the triangle, now we can continue our proof. It's just for an example. And after this, by the Gauss Criterion, we have just 2 Legendre symbol. And when we multiply this 2 Legendre symbol, we are gonna have this. And we already know the muse. And because of the exponential rule, we have to add this 2 muse. And we already did the muse, so we can take another thing for muse, like p minus 1 over 2 times q minus 1 over 2. And this is the result we expect. So this is our reference. We basically read these 2 books, and that's it. Thank you for listening. And okay.
Thank you so much, Eliz. Is there any question?